Hello and welcome. My name is Paul Briscoe. I'm Chief Architect at TAG, and I'm joined today by my good friend and our CTO, Tomer Schechter. Hello, Tomer.
Hi, good morning, Paul.
Thank you for joining us today. We're going to talk about one of my favorite subjects, interlacing. So just a little background on interlacing for people. Those who have perhaps are young enough to have never encountered interlace, bless you. I hope you never do. In the very earliest days of television, television was a very, very simple system. And it basically consisted of scanning an image in a progressive manner. That is, one line at a time, the image would be scanned, and a little tiny electron beam would scan a photosensitive target and develop an electrical voltage corresponding to the light on the target. And this was the way the picture was encoded electronically. And then elsewhere, a receiving device would replicate that same scanning pattern, but instead of converting light to electricity, it would take in the electrical signal it received and turn it back into light on the screen and paint that picture back onto a screen. The basic theory, I think everyone knows about television. The problem that was encountered was a human problem. Humans have a sensitivity to flicker in their visual system. So if we send repetitive frames at some frame rate, and then we send them slow enough, eventually the human brain will fail to move them into a smooth motion perception, and instead you'll see individual jerking frames of motion. The problem comes down to bandwidth in broadcasting, because there's limited amounts of bandwidth available in broadcasting channels. The technology of the day limited that, and in fact we don't want to use up huge amounts of spectrum broadcasting pictures. So an ingenious technique was developed to essentially provide data compression of the video signal. And it took advantage of this artifact of the human visual system along with one other artifact. And that artifact is that when things are in motion, you can't perceive detail in the motion as much or as readily as you can in a still image. And so actually, an inventor named Theremin, who's actually better known for his musical instrument of the same name, came up with this scheme called interlacing, where the picture was actually scanned twice. The reason for scanning it twice was to reduce the bandwidth, and the way the bandwidth was reduced was by scanning one half of the picture each time. The trick involved here was that it was reducing the vertical resolution by scanning first the even lines and then scanning the odd lines in the picture. So line 1, 3, and 5 would be scanned first time around, lines 2, 4, and 6 would be scanned the second time around. We can now transmit a high enough frame rate that it exceeded the flicker threshold for human visual system. So 50 or 60 hertz flicker rate didn't produce flicker in the human visual system. And it would transfer motion because at this higher frame rate, the motion would be more fluid, even though the resolution would be lost vertically. But that loss of resolution is difficult to perceive by the human visual system. So it was a very neat trick to save bandwidth and actually enable high quality television, which in the day they called high definition TV, in a meaningful manner that could be transmitted in a reasonable amount of spectrum and so on. Now, this little trick brings with it some difficulties. In a world where you're scanning from a pickup tube to a cathode ray tube, this works beautifully. There's nothing in between. But we don't work on these half images in real life. We work on full frames of image. You take a photograph with a camera, or you take a frame with a TV camera, forgetting for a moment that there were, of course, interlaced TV cameras. We work with full frames. So as we approach more modern times where images are now progressive and we try and deal with them in that way, and we deal with them inside computers and memory and so on, we need to find a way to get in and out of this interlaced format. Now, why interlaced format? Why does it even exist today? Why have we brought it forward into HDTV? Well, the reason is really the fact that there's countless hours of content already in existence in interlaced formats. That content has to somehow be respected in an ongoing way for ongoing usage, especially historical and media and archival footage. The other challenge was, of course, when the HDTV era came, we needed a fast way to evolve into HDTV and to move everything from interlaced to progressive pictures and move the resolution from SD to HD and move the broadcasting medium from analog to over-the-air digital and so on was too big a step. And it was felt that keeping interlaced formats alive was an important thing. So HDTV today contains interlaced formats still. I'm pleased to announce that UHD TV doesn't. So in the process of doing this very, very simplistic, very early technique, we come up with a whole bunch of challenges that have to be overcome in order to integrate that into a modern production environment where we deal with progressive pictures and we deal with evolutionary frame rates and evolutionary resolutions. We still have to somehow accommodate this stuff, and the 2022-6 standards accommodates it. The 2110 standard accommodates Interlace, and Interlace isn't going anywhere fast. You probably have it in your life. If you go home and watch TV, you certainly have it somewhere between you and the TV station. And so we'd like to talk a little bit today about interlacing, how it works, and some of the challenges associated with handling interlace. What do you think, Tomer? How do you feel about telling us a little bit about interlacing, and in particular, de-interlacing? Because the first thing we need to consider is how do we get an interlace signal down to a progressive picture? Because this is a difficult challenge. Can you talk a little bit about the quality involved, how deinterlacing works, and the quality of deinterlacing, and the different kinds of deinterlacing and where they're used?
Yeah. So, of course, it depends mainly on how you get your content and how you display your content. So the content can be originally created by an interlaced source, maybe a native interlaced camera, but it can also be created by transcoding of progressive content into interlaced feed. And then later on, of course, it's very important how you're going to display it. Today, all of the displays that we have are progressive displays. So in the end, everything is displayed progressively. Now, the de-interlacing can come between the last point, the player to the screen, in the screen itself. It could be on the player if it's a laptop or a computer. It could be maybe somewhere on the transmission flow. So it could be in different places, but in the end, the user will watch a progressive frame. Even if it's transmitted as interlaced all the way, because all of the LCD screens, all of the new screens are progressive scanning only. So somewhere in the middle, if you have the word interlaced, you have the interlacing. If you're not doing the interlacing, you just display the two fields, you'll see a chainsaw signal every time that you have a motion, horizontal motion. On the vertical side, you don't have a real effect, maybe in moving lips and so on, but usually on vertical movement you see it. If you're watching a soccer game, it's very clear. You'll see the lines of the field, either twice, or also if you have bad de-interlacing algorithm, you see two lines instead of one, all of those kind of effects. So how to do the de-interlacing? There are different methods how to do it. In the end, we're talking about having two fields encoded on separate times. So we have the odd lines of one timestamp and the even lines of another timestamp. So the camera is taking a picture of a different content in those two times. This is why you see the lines in the football game twice. And the algorithm for the de-interlacing can be, there's lots of different algorithms. So the basic, most simple one will be just to do averaging of the two fields, and then you'll see smears in between, and you'll see all kind of weird artifacts if you have movement. And also, if you don't have any movement, you will not have a high quality because you're averaging the information. So another more sophisticated way to do it is to detect movement and to align the lines between the fields based on this movement. This is still not considered motion compensated de-interlacing because you're just doing horizontal alignment. You don't move stuff between the lines. So each line is you just slide it to the sides and find the right position for it. This usually creates kind of very good quality, but not so good for still slides. Because still you have the issues of the different positioning of the lines. And I think that the more sophisticated one is really to do a motion compensated algorithm where you detect specific items moving in the frame and do the interpolation of all of the missing information. Then you'll probably have the best quality for the moving stuff in the image. But all of those algorithms are interpolation algorithms, meaning that they can introduce errors or artifacts to the picture if they're misdetecting what's going on in the picture. So it's again, all of the deinterlacing algorithm are creating 50% of the content from nothing.
It's interesting too because there's a cost point associated with each kind of deinterlacing, and it's proportional to quality. And to show my age and go back a few years, there was a time before HDTV when the toughest conversion was frame rate conversion from Europe to North America, for example, and particularly sporting events. And motion compensated frame rate conversion was available. And the cost of a single channel of live hardware to process that exceeded $100,000 US at one point, just because of the uniqueness of the product and the technology inside to actually do that motion estimation, back in the 1990s, for example, to do that kind of motion estimation and motion correction and develop motion vectors with the technology of the day was a handful. So really quite incredible how the price of deinterlacing for that kind of process just escalated with quality. Today, of course, we can get very, very high quality for a much lower dollar cost. And we can do it all, of course, in software, and we can do it offline. But at the end of the day, it's an imperfect process, right? You cannot deterministically return to the original picture. All you can do is use a very, very intelligent system to get really, really close. It's kind of interesting. So when we combine that with scaling, both either in front of scaling or after scaling, it's going to have some concatenated impact on the quality. Can you talk to that a little bit?
Yeah. So when we're downscaling, we're effectively dropping information. So it's not really a problem, because if you invented some information and you drop some information, you're in okay place. Of course, you need to try and drop the invented information and not the real one. But when you're talking about upscaling, then the upscaling itself, again, is interpolation of the information that you have. The deinterlacing is another interpolation. And the combination of the two together is a huge interpolation. And what you really have in the original content is just a very, very tiny piece of what in the end you have in the whole picture. So in those cases, it can be quite a degradation of the quality in the end.
And this is a bigger problem today, because in past times when the entire production system was built on interlace, there was never a need to deinterlace, process as progressive, and then reinterlace. But today, of course, you go into production processes where you have no choice but to deinterlace to do whatever production step, perhaps compositing of live action animation or live sets, something like that. And you can only really do that effectively at progressive. But what it means is sometimes in a production distribution chain, you will have more than one deinterlace, reinterlace, and perhaps even scaling go on. And so it means that you can very, very quickly degrade your picture in a production system if you're using an interlaced infrastructure. To talk a little bit about use of interlace versus use of progressive in production systems, both in the production system equipment, but also in the distribution infrastructure.
Yeah, so I think that all of the usage of interlaced in the production systems is just old installations and usage of old equipment. There's no real reason today to start a production with interlaced content. But of course, if you already have cameras in place and you have everything going on, your content will come to the production site in interlaced formats. And as you said, the visual effects and filters that you can create on interlaced content is limited, especially if you want to create the same content in multiple frame rates. Doing frame rate changes on interlaced content is a lot more complex than doing it on progressive content. So this is where you'll have the most of the problems. But again, if the content is coming as interlaced and it's a given, it can be, maybe even the source itself is progressive, but you have some long-haul delivery of the content, which you already have it in place and it's only supporting interlaced formats, then you'll have it in interlaced. And then usually you will de-interlace the content in order to do all the graphics and add everything and so on. And then in the end, maybe if you still have customers with old set-top boxes which support only interlaced, then you'll go back to interlaced output encoding. But usually in between, even if you're shooting the game in interlaced and delivering it to the customer in interlaced, in the middle, you'll probably work in progressive modes.
Sure. And we'll talk about this in a few minutes, but of course, by the time you get to the final point of consumption, you're going to deinterlace again for display. So if you've deinterlaced already upstream once, you've already set this picture up to be degraded, upon viewing. So yeah, it's complicated when you start to mix the two. The one thing about production systems I will mention is there's a ton of content, even in HD, because we had interlace come over to HD when HD started. There's a huge amount of HD production done in interlace, so there's still a lot of archival content that is meaningful, not just old news clips that are okay to look like old news clips, but other content that's actually, it's there in the archives in interlace, and we have to deal with it. Maybe it's a good time to just mention film. Film is an interesting challenge. Film runs typically at 24 frames per second. And of course, television doesn't, especially in North America, where we just have to be different and run it at 23.98. So talk a little bit about how film was handled with telecine processes using interlace, because interlace was a really useful, tricky way to handle film in television, wasn't it?
Yeah. So film is 24 frames per second progressive scanned. And when you're converting it to interlace format for the American sides, then it's 2997. It's really 60 fields per second. So it's exactly 2.5 times the original frame rate. So there is an algorithm how to create the interlaced format from this 24 frames. It's called pull down, 1.5 pull down, something like that. I don't remember the term.
Yep. Mm-hmm.
But it is not a lossless conversion. So if you know the exact algorithm of how it was done originally, you can recreate the original progressive content out of the interlaced content without doing any interpolation. So this is the only format where it's reversible. When you're talking about the European formats, and it's not, because you are creating an interlaced 25 frame per second content, which I don't have a clue how you really do it from 24. It's both interlacing
you just run it at 25 frames per second and sample rate convert the audio to fix the tone, I guess is what you do. There's another thing that's like it, and we should probably just mention it only because it's confusing, and that's progressive segmented frame, PSF format, which if you look at the data stream, looks like interlace, but it's not. Tell us quick what PSF is and how it's different. So
there is, for interlaced, especially when you're talking about, of course, the uncompressed formats, the SDI or the 2110, 2022, then there is two levels of how you handle the content. It's the content itself, whether the content is interlaced based on fields or not, and how you deliver it. What is the carrier? And it's possible to send a progressive frame over an interlaced carrier. The reason to do it is you can just use equipment which supports only interlaced carriers, and you still can push progressive frames over it. In reality, if you really try to display those frames, then you'll have lots of jitter and stuff, because it's not really based on fields. But it is a progressive frame which is sitting in an interlaced carrier. As long as the two sides of the transmission knows about it, it works quite well.
Right. Sure. And if it's arriving, well, if you have interlace that's arriving and a receiver thinks it's PSF or vice versa, it'll misprocess it, of course. But yeah, it's a small, confusing little aspect of interlace, but it's a handy inclusion in the use of interface to be able to carry a progressive frame using PSF. So for people with interlace systems, there is a way to accommodate progressive in your system design if you can't avoid building in interlace. So interlace is everywhere. We have these sources. We of course are interested in monitoring them because that's what we like to do here at TAG. Talk to me a little bit then about the considerations in monitoring interlace sources in a multi-viewing and probing system.
Okay, so before talking about the monitoring side, we'll talk about how it's being delivered to the customer. because in the end, you're delivering compressed content to the customer. And when you're talking about compression, different compression algorithm codecs are handling the interlaced content in different ways. So for example, MPEG-2 can handle the compression based on fields. So it compresses a whole frame, but does handle the fields together. And for example, HEVC doesn't handle a whole frame. It handles separate fields. So the whole behavior is completely different. So for HEVC, for example, you get fields one by one on the output, and for a MPEG-2 and H.264, you'll get complete frames. So you don't get the fields one by one, you have the whole frame. It's a complete different behavior. And this is also relevant for the monitoring side, because on the monitoring side, you would like to monitor both the uncompressed and the compressed. So if you're monitoring compressed content, which is receiving interlaced content, but is received as whole frames, you don't have the ability to handle each field on its own. So you lose some of the latency in this case because you have to wait for the whole frame. While for uncompressed content, you get the fields one by one. So on the 2110, on the SDI, the fields are sent one after the other. You have the whole amount of even lines and odd lines and vice versa. So it's a different behavior of how to synchronize everything all together. Now, the main problem with monitoring is that you would like, first of all, not to show something that is not real, not to fix problems and not to generate problems which you don't have on the source. You want to give the ability for the viewer, the operator, to understand if he has fluidity issues with the content or not. And that's where the sophisticated deinterlacing algorithms come into play. If you have a very good algorithm how to do the deinterlacing, it might fix fluidity problems of the content because it regenerates the motion and everything. And if you have reversed fields or any other issue, it might be fixed by the deinterlacing. But if the multiviewer is doing this deinterlacing, the monitoring system, but it's not doing the same algorithm for the customer, then the customer might see something which is completely different. Another complex issue is the combination of different frame rates. If you're combining different frame rates with interlaced sources, then it's a quite of a difficult way to do it if you're talking about interlaced content. So if you have a 25 frames per second interlaced input and you're creating a mosaic in 25 frames interlaced output, and suddenly you want to push 2997 into this multiviewer, then you have a real problem because you need to deinterlace, reinterlace, and do lots of stuff on the content. And in the end, of course, as we said, the screen will be a progressive screen. It will always be a progressive screen. So it never makes sense to create the monitoring, the multiviewer in an interlaced format. It only makes sense to create it in a progressive format. So you have less processing on the monitor side. So this behavior, this workflow takes one parameter out of the equation because different screens doing the deinterlacing in different ways. And if you don't do the interlacing on the screen, you just have a more persistent behavior of the system. So the best way is to receive the interlaced feeds into the multiviewer, to do the deinterlacing on the mosaic creation and send a progressive output either at the same frame rate or double frame rate, depends on lots of parameters, but either 25, 50, 60 frames per second.
It's interesting what you say, because of course in viewing and monitoring from a technical, creative content point of view, you want picture quality, you want to make pretty pictures. In multi-viewing, it's not intuitive, but you really don't want a fancy deinterlacer that hides things. You want a deinterlacer that cleanly deinterlaces but does no more. So you accurately can replicate what's really being conveyed in the signal. And so it's kind of counterintuitive because we normally think of putting the best deinterlacing possible at every point in the system. And by design, we actually don't want to go too far in deinterlacing and fixing the picture necessarily, because the whole point of the system is to convey that to somebody that there is something to look at. Interesting also about interlaced outputs, there is a case, we've encountered this, I've encountered this a couple of times, where someone is living in an interlaced production system and they wish to actually re-enter their routing system with the output mosaic. And that means that the output mosaic then has to not only be interlaced, it has to be timed back into their system to be a time source into their router. So there are cases, I think, where we encounter that, but certainly it's good to discourage. I mean, basically, any temporal processing you do with the picture is not going to be a good thing because of the predictive nature of it, right? So that's interesting. Talk to me a little bit about panels then, because, I mean, this is an interesting thing because there's a lot of knobs and switches in panels to turn on processing to make pictures smooth and make them, bright and shiny and fancy and make you feel good about the price you paid for your TV set. Talk a little about these features, what they do to especially to interlaced content, and why you turn them off.
Yeah, so we lost a few R&D days in our lab because of screens, because of the panels and the processing that they're doing. As we found out, many of them has game mode where it disables all of the processing and kind of convert it into a PC monitor. Also lowers the latency. Those processing also increase the latency in most cases by 2 frames. But we did see that even when you disable all of those features, you still have all kind of potential artifacts. For example, a multiviewer is a set of different boxes with borders, very strong borders, which is kind of not a common video content. And usually screens will try and detect global motion of the picture and do all kind of corrections and stuff. And those borders, which are not moving, while the content of those tiles do move, is something that is not native to the screens. And in many cases, we got complaints from customers sending us screenshots of the borders of the mosaic moving. And we had to debug it and explain that this is done on the screen, that if you open the same content on another screen or on your laptop or on a PC screen, then suddenly the border stays in the same place. So you do see all of those kind of effects. On some screens, the game mode really fixes the issues. On some screens, some panels, nothing really fixes the issue. It's like hard-coded into the screen. So usually using large PC monitors, if available, will give you the best quality. Of course, if you're going to the 60-inch screens, and those are not available, and then you really need to test your screen before deciding what you're going to use. It's not based on brand or quality or price. Of course, this is relevant for consumer screens, and if you need 200 multiviewers in your facilities, then you'll probably use consumer screens because professional screens will be too expensive for this amount. And then you need to do a POC and decide if your screen really gives the behavior, the qualities that you would like to see. And again, in the end, if you do see some kind of an artifact, you should check it with another screen to see if it's really coming from the screen. You need to be familiar with what artifacts are created by the panel and what are part of the content.
This is an interesting change in our industry because the old funny term in air quotes, broadcast quality, has been dissipating over the years. But interestingly, where we used to always build TV stations and control rooms with broadcast quality monitors, usually built by a broadcast equipment vendor, fast forward to today where people are quite happy to fill control rooms with what I would call high-end consumer or prosumer monitors, simply because of the price point and the fact that unlike fabricationable TV sets where the quality of the CRT and the electronics and everything made a difference, panels and things like that, the electronics to process for them are all commodity today. And the quality that comes out of these monitors can be as good as a professional monitor for the most part. Certainly not for color grading, certainly not for critical monitoring. So we're now seeing a world where you actually have to qualify your monitors very deeply in a proof of concept in a lab for things like motion artifacts as well as color rendition and so on. But it also opens the door to people to not have to buy exceedingly pricey monitors anymore to build control rooms. They can now take advantage of the wealth of consumer electronics that's out there if they do so with care. I need to interject something. I'm such a terrible host, and I'm so sorry. I'm sure there's questions. If people have questions, please type them into the chat box. We have that being monitored by our crew, and when we get to the end here, we'll be happy to answer any questions that are posed in there. Also, Tomer, something occurred to me as we're going along. I just wanted to re-mention here, because latency in live is so very important. And I think we have to mention that when we do live production in pure interlace, let's say in the analog days, or even in the SDI days, the latency is not really a factor as a result of the format. So we're pushing fields through the system, they're all displaying in real time in the control room, and so on. When we move to interlace, every time we deinterlace, we actually have to stop video long enough to get the second field coming in order to be able to do the interpolation, the motion estimation, and so on. So deinterlacing and reinterlacing inherently introduces latency into your system. So if you are going back and forth from interlace and deinterlace processes, from progressive to interlace, be prepared to accumulate some latency and understand where that's coming from. There's one other thing then that's really quite puzzling to me, Tomer, and you'll know this quite well. The compressed domain. We've all been talking so far about baseband pictures. Pixels on the wire, all one after the other, all lined up nicely and easy to understand. When we go into compressed, and there's many compression formats, interlace has to be a mess. Tell us the whole story about interlaced in compressed formats.
Yeah, so this is quite nice and interesting. When we're going back to MPEG-2, where the real professional compression started, then interlaced is a native part of the content. The content is encoded as macro blocks. It's a 16 by 16 pixel blocks. And for progressive content, the scanning is just like that, going between the lines and down. And for interlaced, it's doing the same thing with jumps of lines. So we're doing it, the macro block is based on 16 pixels on 32, and one macro block will be the odd lines and one will be the even lines. So it's kind of native in the content, because if you're, the reason to do it is because if you're taking a block of interleaved fields, then you the chainsaw effect between the lines will consume a lot of your bandwidth, because it's not persistent content. So you take each field separately in the end. So this is for MPEG-2. In MPEG-2, you also have the ability to move dynamically between frames which are interlaced or progressive in some cases, again, because for still slides and where you don't have a lot of motion, you get better quality on progressive compression, because on interlace you have in the end 2 frames. You have the 2 times the same content. Now, when the industry evolved to, for example, we'll take HEVC, which is a big jump in the technology. And HEVC was mainly designed in order to reduce the bandwidth for UHD content, which doesn't support interlaced. And later on was also used for mobile devices where you want very low bandwidth usage. In those 2 cases, you don't need interlaced because you don't have the interlaced content. But then when it was adapted back to the broadcast industry, the mainstream of the broadcast industry, you suddenly had to support 1080i, but it doesn't support interlaced content natively. So HEVC can only handle interlaced content as 2 separate fields. So it encodes each field as a separate frame. So it doesn't have any native understandings that the content is interlaced. It means that you lose on the bandwidth, on the compression, and it also means that you need to decode 2 separate frames in order to create your original interlaced frame. We see the same thing in the J2K and in JPEG XS. JPEG XS is the same as HEVC. It also doesn't have native support for interlaced content. So again, you're encoding 2 different frames which are based on a single field. There is additional downsides in this, because if you're only encoding odd lines, it means that the difference between the lines is not fluid. Again, you have a gap of a line. So you always have bigger gaps, and you have a lot of more information to quantize. So you lose some of the bandwidth, and also you eventually lose some of the quality, because bandwidth is something which you try to preserve.
Shouldn't be surprised that modern compression formats don't accommodate interlace natively. And probably not a bad thing. I'm not sure it's something we want to engineer, a longer life for, but it certainly makes it difficult. So then basically in compressed systems, we really want to stay away from interlace as much as possible and simply always use progressive imagery. Is that right?
Yeah, the qualities that you'll get, and again, when you're talking about compression, quality is a parameter of quality and bandwidth. It's one instead of the other. So for the same bandwidth, the qualities that you'll get will be better for progressive content than interlaced content.
So coming back to monitoring then, can we just go over the sort of best practices for multi-viewing of interlaced content in either a progressive or a mixed production environment? I think what I've got so far from this is, first of all, we want to convert everything into progressive inside the multiviewer. Is that right?
Of course, you don't have control on your sources. If your sources are interlaced, that this is what you will push to the multiviewer. You will not want to convert it externally before pushing it to the multiviewer because it's additional equipment and additional points of failure where you don't really know what's going on, what might happen. On the output side, of course, your screen is progressive. You want large, nice LCD screens for the multiviewer, so it has to be a progressive screen. So again, you don't want the screen to do the interlacing because it doesn't produce persistent behavior, especially when your content is based on tiles. So you want to push progressive content to the screen. So it means that your monitoring system, your multiviewer, has to receive interlaced content and create progressive output. So the only parameters that you have a flexibility to decide is whether you're going out in the same frame rate on the output or double frame rate, meaning that moving from, for example, 29 frames interlaced content into 29 progressive or 60 progressive, where you have higher quality, higher fluidity, potentially. But the downside is, of course, bandwidth on your network and more expensive devices.
Yeah, and more complicated deinterlacing because instead of deinterlacing two fields into a frame at half the rate, you're now actually deinterlacing two fields into a stream of frames that you're outputting at the field rate. So it's even more complicated considerations. So is there any future for interlaced video? Do you think there's anywhere it can go, or is it really something we need to support and accommodate as it winds into the sunset?
No, I think that it's the time for the interlaced. It's finished. It's already on its last few breath. It's once the minute that they stop selling interlaced screens, then there's no real reason to continue working with interlaced. Today, even if you really want to do a test of something with an interlaced screen, native interlaced screen, it will be very difficult for you to find one.
It's funny. It seems on the customer base, just about everybody I know has one or two CRT monitors still in their facility for that case of they cannot understand what they're seeing on a signal, and they go and they look at it actually on a real CRT monitor, which is displaying real interlace, and only then is the truth revealed. So from an analysis point of view of interlaced signals, it's interesting how the old tool is still handy. But I do agree with you. I think interlace is a legacy compatibility we're going to see declining going forward. We also have to remember, however, that a lot of the world is still broadcasting. Not everybody is moving to UHD TV over the air. HDTV is still not entirely prevalent across the planet. So there's still other places where interlace still exists, and of course we know this from our customers and from the queries we get. And interlace isn't our biggest problem. It's kind of nice to put it aside, but we still have in North America and other places frame rates that are modulated by a factor of 1.001 from their native rate, and maybe that's our next challenge, to try and flush out from the history of broadcasting and not take that forward too much further. Anyway, I don't know how we are for questions in the chat box. We have our team watching that list there. Do we have any questions that have popped in? So, here's a question. So what is the best kind of deinterlacing technology to use for critical program paths, and why? Maybe you could just go over that again there, Tomer.
Okay, so it depends. It's two separate use cases. If you're talking about the interlacing in order to send progressive content to the customer, so you need the best interlacing algorithm with motion compensation, estimation, and everything, and recreate something from something that you don't have. But if you're talking about the interlacing for the monitoring device, then you want exactly the opposite. You want the minimal interpolation, minimal logic in your algorithm, while still creating a video which is fluid enough, which doesn't seem as interlaced in your eyes, which is usable, doesn't really interfere with the workflow. Because if you have something which is too complicated, too sophisticated on your monitoring device, it might fix problems that are being transmitted to the customer.
Okay. And another question, what is field swapping and why does it happen? And what's the effect?
Okay, so as I said, on SDI, the fields are sent one after the other. So it sends all the odd lines and then all the even lines and so on. Some devices don't know really to sync on the right field. So you can decide that field 1 and 2 are a frame or field 2 and 3 are a frame. If each field has its own vertical position, so it always will be in the right place. But if you have the wrong fields, it means that you're changing the timing of the field. So the previous field will be shown before the next field, or in another way. So effectively, if you have a football game and you see somebody running, it will be like that. It will move back and forth because the fields are on the wrong timing. Now, if you have, in some interlacing algorithms, they will solve this issue. You will not see anything wrong with the picture. If you have a CRT TV that receives the content, you will see it, definitely. It will be really visible. If you have an encoder compressing this content, again, it might fix the issue, but it also might be so hurt from this issue that the bandwidth will be so high that the quality of the video will be beneath understanding of what's going on. So in the end, if you're looking at the compressed content, you might not understand that it was field inversion. You might think that something happened, but because the quality will be so low, but you don't know that the codec had to waste so much bandwidth on these inverted fields.
Okay, that makes sense. Very interesting. So we've used up our time. Well, we've gone over time a little bit here. Sorry for that. But I'd like to thank our attendees for joining us today. This is a troublesome topic for people, especially for newer entrants into the industry. For those of us who are baked into Interlace, it's something we've just always had to deal with, and it's a bit of a mystery to more modern media science people. So hopefully we've shed a little bit of light on it. And of course, we're happy to help you with your questions around Interlace or anything to do with monitoring and viewing. Please feel free to give us a call. We're happy to demo our product to you. We can have you up and running with a cloud-based demo before too very long, and you can play with Interlace formats on your own and see how that all works. Tomer, I thank you very much for joining me and taking the time today to do this. It's getting towards the end of your day there. I hope you have a very nice evening.
Yeah, thank you, Paul.
And from Toronto and Tel Aviv, bid you good morning, afternoon, or evening, wherever you are. Thanks for joining.